Welcome back, grade 10s. In today's lesson, we are going to continue on the topic of transverse pulses and waves. We have finished discussing transverse pulses, so in this lesson, we are going to focus on transverse waves. Now, we learned that a pulse is a single disturbance that moves through a medium. A wave, on the other hand, is a series of disturbances. So a transverse wave is made up of a series of transverse pulses. And remember that a pulse either has a moving crest or a moving trough, but a wave, a transverse wave in particular, will have crests and troughs moving through the medium. So here we can see a crest, and here we can see a trough. And in between the crest and the trough is the equilibrium or the rest position. The distance here, which is known as the amplitude, from the equilibrium position to the top of the crest, is going to be equal to the distance from the equilibrium position to the maximum disturbance or the bottom of the trough. Now, in reality, waves do lose energy, so their shape will change and their amplitude will reduce with time. However, in all our examples, we are going to assume that the wave loses no energy. So let's define a wave. A wave is a regular and continuous disturbance that moves through a medium. Remember that we defined a pulse as a single disturbance that moves through a medium, and a wave is a series of pulses, so it's a regular and continuous disturbance. Let's define specifically a transverse wave, and that's now related to the shape of the wave. A transverse wave is a series of disturbances where the particles of the medium move perpendicular to the direction of the propagation of the wave. So remember, when we defined a transverse pulse, we learned that it is a single disturbance where the particles of the medium move perpendicular to the direction of the propagation of the pulse. The definitions are very similar because a transverse pulse and a transverse wave have the same shape. The difference is in the number of disturbances. So in the case of a transverse pulse or a transverse wave, the wave propagates in a particular direction along the horizontal, in the x direction. And the particles of the medium that are carrying the energy are moving up and down in the y direction in relation to the direction of the propagation of the wave. Examples of transverse waves include water waves. That will be the most commonly brought up example on tests and exams. Electromagnetic waves or light waves, which we'll learn about. And then there's certain seismic waves, which are underground waves that result in earthquakes that have a transverse shape. Let's compare transverse pulses and transverse waves. A wave shares some properties with a pulse, but it also has some additional properties that we need to be aware of. So firstly, both a wave and a pulse involve the transfer of energy through a medium. We know that a pulse is a single disturbance while a wave is a continuous series of disturbances. A pulse has one crest or one trough, while a wave has a series of crests and troughs. We learned about the amplitude of a pulse, and I briefly described the amplitude of a wave. Both a wave and a pulse have an amplitude, and amplitude is measured in meters because it represents distance. Recall that the amplitude is the distance of the maximum disturbance of the medium from equilibrium or rest position. So that was a definition for amplitude that we defined in the last lesson. Now, in the case of a wave, we have two amplitudes because we have one amplitude which is from the rest or equilibrium position to the top of the crest, and then we have another amplitude from the rest position to the bottom of the trough. Often on tests or exams, you will be given this distance over here, and you need to realize that that represents double the amplitude. And like I already mentioned, this distance will always be equal to this distance. The fifth point is that a pulse has a pulse length, while a wave has a wavelength. A wavelength is a very important concept, and you need to know this definition word for word, including the part in brackets. The definition of a wavelength is the distance between any two successive points, meaning one after the next, that are in phase, meaning that they're in the same position on the wave. For example, the distance from crest to crest, or the distance from trough to trough. Let's take a look at this diagram. Here we have two successive points that are in phase, represented by the distance from a crest to a crest. And here we have two successive points that are in phase, represented by the distance from trough to trough. It doesn't have to be the distance from crest to crest or trough to trough. Any two points that are in phase with each other, and they have to be successive, meaning one after the other. So if we start our wave motion here, the full wavelength will end here. However, the distance of the wavelength is a horizontal distance. It's a straight line. It doesn't take into account the curve. If we start our wave motion here, then a full cycle will end here. So this distance over here would represent a wavelength. A wavelength is represented by the Greek symbol lambda. It's measured in meters because it is a distance value. The wavelength is very often, but not necessarily, measured as the distance between two crests or two troughs. Points that are successive and in phase are separated by one full wavelength. We may think of a wavelength as a full cycle. If it's not separated by full wavelength, so if you have 2 points in a wave that are not separated by a full wavelength, then they're not in phase, they are out of phase. So from the graph below, I'd like you to identify any 3 points that are successive and in phase, meaning that they represent a full wavelength or a full cycle. So I came up with these: D and I, C and H, B and G, A and F, and E and J. All of these points represent a full wavelength, so they're in phase. If I consider C and D, those 2 points are out of phase. C and I would also be considered out of phase. E and G would be considered out of phase. If I consider point A to point F, that represents a full wavelength, a full cycle. If I look at point A to E, well, they're out of phase because they don't represent a full wavelength, but actually this distance over here would represent half a wavelength. We're going to come across past paper questions where this will become apparent. If we consider the distance from the top of the crest to the top of the next crest, well, this distance here represents a full wavelength. But if we consider a distance from the top of the crest to the bottom of the trough, that again would represent half a wavelength, half a wave cycle. Number 6 is that a wave has a period and a wave has a frequency, and a pulse does not have either. Now we're going to learn about the period and the frequency of a wave in detail. Number 7, a pulse has pulse speed. It uses pulse length in the calculation. A wave has wave speed that uses wavelength in the calculation. And again, we're going to learn about that in more detail once we have learned about the period and the frequency of a wave. So let's now move on to defining the period of a wave and the frequency of a wave. Let's start off with a period. Imagine you are sitting by a pond and you are watching waves move past you. You see a crest at one particular point in space. You start your timer. You stop the timer the moment you see the next crest pass the same point in space. Now, this amount of time that it took to get from one crest to the next crest is called the period of the wave. The period of the wave represents the time that it takes for one full cycle to pass a certain point in space. The period of a wave is simply represented by the letter T because it is the amount of time that it takes for a full cycle to pass you by, and time is always measured in seconds. So let's define the period of a wave. It is the time that it takes for one cycle, for example, 2 successive crests or 2 successive troughs, to pass a fixed point. Let's now discuss what the frequency of a wave means. Now imagine you're at that pond again. As you see a crest, you start your timer. But you stop your timer after 1 second. The number of crests that you counted in that 1 second is the frequency of the wave. That really means cycles per second. Frequency is how many cycles manage to pass by a certain point in 1 second. Frequency is represented by the symbol F, and it's measured in hertz. But in your minds, you should always convert hertz to cycles per second because it's easier to make sense of what frequency means that way. So let's define the frequency of a wave. It is the number of cycles, e.g. successive crests or successive troughs, that pass a given point in 1 second. Now, what we need to understand is that the frequency and the period of a wave are inversely proportional. What that means is that frequency can be calculated as 1 over period, and period can be calculated as 1 over frequency. So, for example, if the time between 2 consecutive crests passing a fixed point is half a second, then that is the period of the wave, because a full cycle takes half a second. So we may calculate the frequency using this formula over here. We've got the period, so the frequency is 1 over period, which is 1 over 0.5, which is 2 hertz. So that means that if a cycle takes half a second, then in 1 second we get 2 cycles. That is what we mean when we say that frequency and period are inversely proportional. So again, if it takes half a second for one cycle, then in 1 second, you'll get 2 cycles. If the number of cycles that pass a given point in 1 second is 2, then that means that the frequency of the wave is 2 hertz, because that means 2 cycles in 1 second. Then the period of the wave must be 1/2, which is half a second. So this means that if 2 cycles pass you by in 1 second, 2 cycles per second means 2 hertz, then it takes half a second for a full cycle, which is then the period of the wave. This inverse relationship means that a wave with a higher frequency has a shorter period. A wave with a lower frequency has a longer period. That is what an inverse relationship means. A higher frequency leads to a shorter period, and a lower frequency leads to a longer period. And I'd like to explain that in a little bit more detail now. Let's take a look at these 2 transverse wave graphs to make sense of this relationship. Here we can see that a full cycle, this is a full cycle, and that takes 2 seconds. Whereas a full cycle over here takes 4 seconds. So the period of this wave is 2 seconds, and the period of this wave is 4 seconds. Now we may calculate the frequency of the wave as 1/t. So in this case, it would be 1/2, which is half a hertz. And in this case, it would be 1/4, which is 0.25 hertz. Now remember that frequency is how many cycles can fit in 1 second. So here we've got half a cycle in 1 second. Over here we have a full cycle in 4 seconds, therefore half a cycle in 2 seconds, therefore a quarter of a cycle in 1 second. So that should make sense using logic as well. Now, over here, because the crests are closer together, it represents a higher frequency wave, whereas this over here represents a lower frequency wave. Here we have half a hertz, and here we have a quarter of a hertz. So this one is higher frequency than this one. Now, here we have a high frequency wave and a lower period, and here we have a lower frequency wave and a higher period. So that just confirms the relationship that a higher period means a lower frequency, or a lower frequency means a higher period. Both of those mean the same thing, and they show the inverse relationship between period and frequency. This brings us to wave speed. We define speed as distance traveled per unit time. So the equation for speed is distance over time. Now, in the case of a wave, the distance is the wavelength and the time is the period. And that is why the wave speed is the wavelength of the wave divided by the period of the wave. We may represent it as the symbol V for wave speed is equal to wavelength represented by lambda divided by the period, which is represented by time t. So the wavelength is measured in meters, the period is measured in seconds, and speed is measured in meters per second. So wave speed is the wavelength divided by the period. Now, because the period over here is equal to 1 over frequency, we may replace this T over here with 1 over F, because period is 1 over frequency. And we may rearrange this to get wavelength times frequency. Now, if you don't understand this derivation, it is not important, but I just wanted to show it to you. So again, because frequency is 1 over period, then the wave speed may also be calculated as wavelength times frequency. Or wave speed, which is represented by the letter V, is equal to wavelength represented by lambda times frequency represented by the letter F. Wavelength is measured in meters. Frequency is measured in hertz. Hertz means cycles per second, or 1 over second. So the speed is measured in meters per second. This brings us to the end of our discussion on transverse waves. In the next lesson, we will make sure that we've understood all these very confusing concepts by answering questions. The questions that I have prepared come from past papers. Those examples should really give you some ideas of what to expect on tests and on exams, and they should also give you the confidence to go ahead and practice more questions on this topic.